Good afternoon, everyone. Thank you very much for inviting me to be a speaker at the ISCO UK 2025. In this talk, I will discuss the origins and evolution of today's AI ecosystem and argue that general-purpose categorization systems would be welcome as part of the AI ecosystem, assuming that they are intuitive, easy to use, kept up to date, and free. In 1998, I moved to San Francisco to assume a senior role at a startup company named Data Fusion. The Data Fusion company was the brainchild of Joel Schatz, who had made a lot of money building a mobile telephone network in Russia after the fall of the Soviet Union. He was a proponent of systems dynamics, a methodology and mathematical modeling technique to frame, understand, and discuss complex issues and problems. Joel wanted to build a tool that could visualize inputs, processes, and outputs with knowledge maps. Knowledge mapping is a structured process that visually represents the flow, storage, and access to knowledge within an organization. Joel wanted to develop a tool that could visualize big systems and the relationships between entities, systems related to water resources, air quality, transportation, and world peace. These sorts of systems models needed content, lots of content, and in 1998, lots of that content was not structured much or at all. To make that less structured content useful, we needed to develop a content processing pipeline that could apply language processing methods iteratively to break down the narrative into meaningful chunks and then identify and disambiguate the named entities. Finally, the content needed to be analyzed to determine what it was about and why it was important. Once we had built a highly curated collection and tagged the hell out of it, we could generate visualizations of the relationships among the named entities within the chunks and ultimately construct many narratives. Sounds a little like knowledge graphs and generative AI? It was, except without any of the computing power that we have today. Simply put, n-gram level tokens were out of the question because it was simply impossible to hold a large enough matrix in memory to compute relationships at a very granular level. Indexing is one of the core functionalities of information retrieval. In addition to natural language processing and named entity recognition, we needed to do content tagging at scale. In 1998, a number of information retrieval engines using vector and probabilistic statistical methods were available as open source or as licensable OEM products. Latent semantic indexing and clustering were still primarily in research and development. We opted to implement a vector method because it generally performed better in our testing. The challenge was to build training sets. While we focused on domains where there were readily accessible, well-categorized content such as medicine and law, we were constantly asked to build general-purpose categorizers for common business functions. But at the time, and with the available technology, we failed to be able to do this effectively. At the same time, web search engines were beginning to be available on the fledgling World Wide Web, quickly displacing the Yahoo and DMOZ topic trees for browsing the web. AltaVista was the first web search engine to become wildly popular until it was overtaken by Google in 2000. Previously, online searching was only available through expensive timeshare services or on-site at some research libraries. It was limited to a few published subject indexes, required training and expertise to use effectively, and only got you a bibliography, not usually the full text of items. Web search engines were accessing full-text resources limited only by what was available on the web. Access was free, and the type-and-go user interface was extremely simple. But under the hood, The democratization of online searching was ranking search results by popularity rather than by Boolean searching subject and named entity indexes to find relevant and comprehensive results. While everyone could use Google, not everyone was able to get good search results. Even with the dead simple user interface, choosing effective search terms and knowledge about Google syntax could enable better search results. For many, the new millennium seemed like the golden age for information access. Also in this period, the first Dublin Core Workshop was held in 1995 in Dublin, Ohio, hosted by OCLC and the U.S. National Center for Supercomputer Applications. The original Dublin Core was published in the report of the workshop. In 1997, I organized the first NCOS workshop as part of the second ACM conference on digital libraries held in Philadelphia, Pennsylvania. NCOS stands for Network Knowledge Organization Systems. In 2000, Data Fusion was renamed Metacode. Metacode was the name we gave to the unique identifiers assigned to concepts in knowledge maps. This was an easy implementation of namespaces and universal resource identifiers, URIs, and one of the first instances of assigning URIs to concepts, such as terms, in a controlled vocabulary, of which I am aware. While Metacodes predate SCOS, the SCOS data model views a knowledge organization system as a concept scheme comprised of a set of concepts. We built a vocabulary management tool for creating and managing metacodes, a content tagging pipeline for assigning metacodes to content items, implemented a metadata database for storing metacodes associated with content objects, and provided a graphical user interface for viewing and browsing metacodes in knowledge maps. By the end of 2000, we had a few early customers, and Metacode was acquired by Interwoven, a publicly traded web content management company, for the astounding price of $150 million. Interwoven rebranded the product as MetaTagger, emphasizing the content tagging pipeline for automating the generation of metadata to enable methods of publishing dynamic website content. After spending 2 years building information product domains at Metacode, I spent 2 years working at Interwoven, promoting tagging content with metadata. Think of this as moving from building the art and architecture thesaurus ontology for material culture to promoting the use of Dublin Core metadata for cataloging content. Interwoven was a much larger company than Metacode. I was assigned to work in field sales, which means that I went on calls with sales professionals all over the world to all kinds of businesses and organizations in many different sectors who were all trying to figure out how to do business on the World Wide Web. My job was to promote metadata tagging using the MetaTagger product as part of the Interwoven web content management ecosystem. I had the job title of Content Commando. I was exposed to myriad use cases every day of the week. It was overwhelming and a crash course in business information management. The business organizational concerns about how to make money and stay out of jail may not have been as lofty as Data Fusion's concerns about water, transportation, and peace, but they were more immediately actionable and measurable. One of those sales calls was to NASA's Jet Propulsion Laboratory, JPL, which became the first project of a new company, Taxonomy Strategies, that I would form with my former Data Fusion chief scientist, Ron Daniel. Taxonomy Strategies worked with JPL to develop the NASA taxonomy from 2002 to 2005. In 2003, Taxonomy Strategies created the content model for the first U.S. government web portal firstgov.gov, now USA.gov, and later developed Web 1.0 information architectures for many U.S. government agencies. Taxonomy Strategies also developed the first online shopping taxonomy for Home Depot, a large home improvement retailer, in 2003, and then went on to develop consumer and business-to-business online shopping taxonomies for many well-known companies like Dell, Nike, and Oracle. By applying the lessons learned at Data Fusion, Metacode, and Interwoven, Taxonomy Strategies had the opportunity to work on dozens of projects in various sectors that have helped to make digital assets easy to find, use, and share. In retrospect, the Data Fusion startup company neglected to pay enough attention to certain aspects of artificial intelligence that emerged in the late 1990s. While we made the right decision to focus on natural language processing, we should have taken machine learning neural network research more seriously. But we had a reluctance to embrace black box technology. We were more interested in automatic classification, especially using predefined knowledge organization systems such as NAICS, MESH, and the AAT. We conducted experiments to optimize the process of building training sets. Generally, this required finding knowledge organization systems with well-categorized content. But the biggest challenge was finding discrete training sets, meaning content that was about one discrete concept, and a critical mass of these examples. We didn't attempt to build any machine learning with regression and recurrent processes and processing. And to be honest, we didn't have the expertise to do that in our team. Data Fusion was 5 or 10 years too early to be able to commercialize machine learning. The real resurgence of neural network research didn't happen until 2005, and the graphical processing unit only began to be used to rapidly transform the really large numbers of calculations required by machine learning neural networks in 2010. But Data Fusion demonstrated the value of knowledge organization systems and rich metadata in web content management, even if the automation of its production was rudimentary. While the GPU has provided the computing horsepower for the current generation of AI, the key innovation that characterizes the current generation of AI is a special type of neural network architecture called the transformer. Transformers enable neural networks to keep track of patterns in their input using self-supervised learning on large amounts of raw text generally taken from the internet. This is highly effective for natural language processing and natural language generation, as illustrated by large language models like ChatGPT, Claude Llama, and DeepSeek. These models are trained to analyze text and estimate the most probable word following a given sequence. Because these models are trained on enormous amounts of content, 13 trillion tokens, or the equivalent of 80 million books, more than twice the number of books in the largest research library imaginable, they are very good at the task of language generation. Another remarkable aspect of the current generation of AI is that the user interface is natural language. When you provide instructions to an LLM, it is very reminiscent of a web search engine. In the LLM ecosystem, natural language queries are called prompts, and the generation of prompts is called prompt engineering. You can think of web search engines as examples of so-called zero-shot prompts, meaning that you type in a query and get a response, even though the prompt itself was not necessarily part of the training data for the model. With a zero-shot prompt, there is not necessarily an intention of iterative prompting, hence the zero. But as we know from online searching, the choice of terminology, style, and format of the prompt is very important. Changing a single word can significantly alter the output. Prompts need to be precise, avoid jargon, use punctuation, and be structured like a use case, meaning it should identify your perspective or role, who you are, what you want to know and why, how you desire the output to be formatted. This table illustrates a zero-shot prompt template with some examples of prompts. More interesting than zero-shot prompting is dialoguing with an LLM. This can be by providing a few examples, or it can be through reasoning or thought generation, decomposing a complex problem, providing verification, or a combination of perspectives, and there are other techniques. This table shows a selection of prompting techniques from Instructor, a popular Python library for extracting structured data from large language models. Chat uses interfaces to LLMs, keep a record of each session, and provide an option to start a new chat. This provides an opportunity for some immediate or near-term iteration without any programming. The good news about AI is that everyone is fiddling with it. The bad news is that the results are unreliable. I think it's similar to the experience with web search. Everyone is looking things up. The results are good enough. This search provides answers to simple questions, but it can be frustrating to get definitive answers, find a known result, or do any sort of in-depth authoritative research. To improve the reliability of search, you need to use better search terms. One way to do this is to look for and choose search terms from a knowledge organization system. The same is true for improving the reliability of COS. I remember interviewing an art historian many years ago when I was working at the Getty Trust. I asked her, "How do you use the art and architecture thesaurus?" She answered, "It helps me think." The approaches to integrating knowledge organization systems into prompts are the same as for integrating knowledge organization systems in information retrieval. Incorporate synonyms and quasi-synonyms in the prompt using a domain thesaurus. Broaden or narrow the concepts in the prompt using a hierarchical taxonomy. Provide specific contexts using facets such as content type, geography, language, time, process, or other contexts. While it's possible to manually refer to knowledge organization systems while writing prompts, LLMs integrate with other systems through the context window. The context window is the input text that the LLM can process. LLMs predict the next token based on the input sequence, and by manipulating this input, one can affect the model's output. The ChatGPT context window is capped at 32,000 tokens. A token is roughly equivalent to 4 characters or about 3/4 of a word. But processing large context windows can be computationally expensive and slow. An application programming interface, or API, allows for development of applications that can integrate additional resources, such as knowledge organization systems and search results into prompts. The ChatGPT context window is up to 1 million tokens when accessed via the API. In this context, COS can also be used to guide language generation results by identifying entities in the output, link entities to knowledge graphs, and connect models to knowledge bases, index source content to improve document recall and precision, and annotate output to improve explainability and trustworthiness. Retrieval augmented generation, or RAG, involves searching for relevant facts and inserting them into the context window to improve the model's answers. The approach can be expanded to include various data sources beyond search engines, such as an indexed domain-specific collection, databases, and calendars, making it a complex but powerful tool for enhancing LLM performance. The response may include annotations, such as source citations or bibliographic references from the domain-specific collection content. A good way to think about RAG is as a method for pre-processing LLM prompts to make them more responsive to domain-specific questions. A knowledge graph is a representation of the relationship among named entities. A knowledge graph may be queried in the RAG method to improve the information retrieval with equivalent terms, but especially to provide associative typed related concepts. It can also be integrated as a post-process to an LLM response to identify possible refinements through reasoning, decomposition, verification, and other methods. RAG applications may use information retrieval in different ways. In particular, they may not necessarily index content using knowledge organization systems. They may use vector search to identify similar content statistically without any reference to a knowledge organization system. A better way to achieve more reliable and measurable better recall and precision is to use vectors to map content to knowledge organization systems, and then to use knowledge organization systems to identify similar concepts. The good thing about standards is that there are so many to choose from. The same is true of knowledge organization systems. Bartok, the basic register of thesauri, ontologies, and classifications, a database of knowledge organization systems, lists over 3,700 resources. ISO has more than 900 terminology standards. Some of these are standards about how to create and manage terminologies, like ISO 25964, Part 1, Thesauri for Information Retrieval, Management and Use. Others are standard domain-specific terminologies. It is challenging to manage terminology and vocabularies in various fields, and particularly in biomedical science. Existing systems, like the Unified Medical Language System, or UMLS, has more than 105 sources that are often inconsistent and complicated. This is a big challenge for the AI community. This is a big challenge for developers. They are simply not equipped to deal with the intricacies of assessing and selecting knowledge organization systems and integrating them appropriately into general purpose applications. Large language models make it easy to get to 80% accuracy quickly, which can lead to ad hoc solutions rather than systematic approaches. This is one of the reasons that AI has generally avoided knowledge organization systems. It has been left to consultants to develop custom applications for niche industries where the benefits of a more precise retrieval outweigh the difficulties and costs of knowledge organization system integration and development, or to researchers. However, I think there has always been an interest in a general purpose categorizer for common business functions, just as there is an interest in universal classification systems for organizing content collections, such as the Dewey Decimal classification, the Library of Congress classification, the Universal Decimal classification, the Integrative Library classification, or Integrative Level classification, and others. I would argue that general purpose systems would be welcome as part of the AI ecosystem, assuming that they were intuitive, easy to use, kept up to date, and free. Thank you very much.